In this video, we will look at a system of two connected masses and analyze how Newton's laws apply to them. Consider the following scenario where you have two masses, one sitting on a flat, frictionless surface and one suspended over the side of that surface. The masses are connected together by a cable over a pulley. This example might model something like a mobile crane lifting a load over a cliff or the side of a construction building. As we're focusing on understanding forces on the masses, we're going to make a few assumptions. We'll assume that the mass of the pulley and the cable are light and negligible, and also assume that the pulley is frictionless. This allows us to ignore any forces or energies needed to rotate the pulley and keep the cord from sagging. Now, without knowing the masses of the two objects, will mass 1 on the flat surface slide or stay at rest? Now let's apply Newton's laws and analyze the forces to determine the answer. Let's begin as we did with the statics application by looking at the forces acting on each mass in our system. Let's start with mass 1. Now mass 1 is hanging vertically next to the surface. It has a force of gravity acting on it, which we will call weight 1. Since it's not sitting on any surface, there is no normal force pushing mass 1 back up against gravity. However, mass 1 is connected to the cable, which pulls up on it. We will call the tension in this cable T. If mass 1 is stationary, then Newton's second law tells us that the net force on the mass must be zero, and therefore the tension on the cable must be equal to the weight of mass 1. However, if mass 1 was to move, the only logical direction is downwards. So the direction of the acceleration, if there was any, would be down. We don't expect mass 1 to move sideways either, so there is no net force in the horizontal direction for mass 1. So now let's write out Newton's second law for mass 1 moving in the vertical direction. But first, we need to define a coordinate system. The usual coordinate system defines the upward direction to be positive. But this doesn't have to be the case. We can define any direction as positive. So let's define downwards as positive in this example. This means that Newton's second law for mass 1 is written as the weight of mass 1 minus the tension. Since the two forces point in opposite directions, tension is negative with respect to weight. Of course, the net force is equal to the mass times the net acceleration in accordance to Newton's second law. If we had defined the upward direction as positive instead, we will end up with the following equation where the net acceleration is negative, indicating that the acceleration vector points downwards. Both equations are essentially the same. So let's stick with going down as positive, so we work with a positive acceleration instead of a negative one. So that's a force equation for mass 1. Now let's have a look at mass 2. As mass 2 is sitting on a horizontal, frictionless surface, its weight is pulling down on that surface due to gravity. Naturally, the surface pushes back up via the normal force in accordance to Newton's third law. The net result is no movement in the vertical direction for mass 2. So the force equation for mass 2 in the vertical direction is the weight of mass 2 minus the normal force exerted on mass 2 being equal to 0. Now mass 2 is connected to mass 1 by the cable, which has a tension in it. So the cable is pulling at mass 2 to the left with the same tension as applied to mass 1. These two tensions at each end are the action and reaction forces due to Newton's third law and have the same magnitude but point in opposite directions along the cable. Since the two masses are connected by the cable, if there is any movement in mass 1, then there is a corresponding movement in mass 2 because mass 1 pulls on mass 2. So the acceleration experienced by mass 2 will be the same as that experienced by mass 1, but the direction of the acceleration will be to the left. Since all of the horizontal forces are pointing to the left, let's call the left direction as positive this time. So along the horizontal, there's only one force acting, which is the tension. And of course, this must produce the net acceleration to the left. So what we have now are three equations. If we look at the first equation and the third equation, we see that acceleration and tension appear in both of them. This allows us to combine the two equations and eliminate one of the variables using simultaneous equations by substitution. Since we're interested in finding the acceleration, we can get rid of the tension by substituting tension in the first equation with tension from the third equation. So equation 1 becomes the weight of mass 1 minus the product of mass 2 and the acceleration to give us a net force equal to the product of mass 1 and acceleration. Now we can transpose this equation to solve for acceleration. This gives us the acceleration being equal to the weight of mass 1 divided by the sum of mass 1 and mass 2. And of course, the weight of mass 1 is equal to the product of mass 1 and the acceleration due to gravity. So we now have a solution to the acceleration of the connected masses, which is dependent on the mass of the two objects and gravity. Let's analyze this solution in a bit more detail. So what would be the acceleration if there was no mass 1? If there was no mass 1, then there is nothing pulling on mass 2, and mass 2 would remain stationary on the surface in accordance with Newton's first law. The equation would be 0 times gravity divided by mass 2, which would of course equal to 0 as expected. Now what would the acceleration be if there was no mass 2? If there was no mass 2, then there is nothing holding mass 1 up, and mass 1 would simply fall under the influence of gravity. So it would experience gravity's acceleration of 9.8 meters per second squared. The equation will be the product of mass 1 and gravity divided by mass 1. Mass 1 will cancel out, and we're just left with gravity as expected. So it is evident from the solutions that the acceleration of the masses will range between 0 when the masses are not moving and g when there is no mass on the surface. Clearly, the masses can't accelerate more than the rate of gravity. The actual acceleration will depend on the size of the masses. So for the final quiz, what would be the acceleration if the two masses were the same, let's say 10 kilograms?